Alright class, I figured I'd do something a little bit differently for this quiz too. Rather than post the answers, I'll just show you how to work the problems. You may hear some birds chirping. That's because it's Saturday morning and I'm out on my back porch. So hopefully it won't get too noisy for you. So here's the first questions. Basically all you had to do was look at the Z table and read off which is C. Or you could have used Excel. If you used Excel, you'd have to know which formula to use. So for A, to the left of Z equals 1.90, you'd have norms diff 1.90, and you'd have ended up with 9713. The next one, to the right of something, is 1 minus norms diff. Norms dist, I'm sorry. Okay. So the next one, 1 minus norms dist of 2.28. And you would have gotten 0113. Third one, between 0 and negative 3.2, 2 norms dist of 0, which we do know is 0.5, so I could have just did 0.5. I'll just erase this and do 0.5 minus norms dist to the other thing, because I know it's half of it. So you can do 0.5 minus norms dist of negative 3.22, and I'd get 4994. I realized in grading your papers that some of you guys are having problems with rounding. Okay, so 5 and up, you go up. 4 or less, you go down, or you stay where you are. Okay. Number 4, between 1.11 and 0.44, norms dist 1.11 minus norms dist 0.44. This just equals 0.1965. Okay. And the last question is between 0.69 and 1.93, which we do the exact same way, equals norms dist of 0.69 minus norms dist of negative 1.93, which would give you 7281. Okay. Make sure you do not round until the end, or else you're going to end up getting numbers that won't look like the ones you see here. Okay. So for the first one, 9713. Second one, 0113. Third one, 4994. Fourth one, 1965. And the fifth one is 7281. And just for consistency, I'll also do what I told you guys to do and put boxes around them. Okay. So I have clearly highlighted which ones are my answers. Okay. Okay, so that's the answer to question number 1. It took about 3 or 4 minutes. Okay. Next slide, you'll see what question number 2 asks. Okay. Find the z-value to the right of the mean so that that area is to the left of it. So the first thing you want to do is draw your picture. 0.96 56. There's a line here. This is the Z I'm looking for. I could grab my chart, and if I grab my chart, I'd see that was 1.82. Or I could have done it using Excel. You could have seen equals norms in of 0.9656. And you'd come back with 1.82 for your answer. Okay. For B, we'll slide this up some. B is very similar, except the answer inside is the area inside is 0.7157. I again can grab my table and see that Z is 0.57. Or I could use my norms INV 7157. And would still come back with 0.57 as my answer. And I would box it. Okay. Now for C, there's actually an error in my question that only one of you guys found. I was surprised, because most of you guys got the right answer, even though I didn't ask the right question. It says find the Z-value to the right of the mean so that 99% is to the left of it, or is to the right of it. Well, in order to have more than 50% to the right of it, I have to be less than 0. So there's a typo here, and you noticed it up here. It was find the area to the right so that such and such is to the left of it. What I meant was find the area to the left of the mean so that that amount is to the right of it. Okay, so this should have said left. Okay. So if you did it and you had a positive or a negative value, but the actual raw number was correct, the absolute value was correct, I went on and gave you credit because the error was mine and not necessarily yours. But I'm going to solve this as though it said to the left of the mean. So I have 99.45 to the right of it. Okay. So if I did that, I would have equals. I'm actually going to still slide up just because I need some more space. Okay. Okay. So the first one was 99.45. I'll draw my line here, and I'm just going to show you how I would do it. Since I want everything to the right of it, the area I have is to the left of it, so I have to do 1 minus. And I'm looking for the Z value, not the area. So I would do equals norms INV 1 minus whatever you see inside. Enter. So, and I'll just call this one A. So for question number C, A is 0.9945, and so my answer would end up being negative 0.254. For B, A was 0.6141, and so my answer would have been negative 0.29. And for C, A is 8830, and the Z is negative 1.19. Okay. So here are your answers for C, D, and E. Once again, if you said 0.29 or 1.19 or 2.54, I went on and gave you credit because, well, it was my fault, not yours. All right, let's go to slide number 3. So here, we're giving a specific distribution, which is 4012. Now with the area between 4924 and 2284, I'll set this up as though this was an Excel problem. And all I want is norm dist, okay? not norms, because, well, I have an actual value here. Get the biggest one first. So I'll do 49.24, comma, 40, comma, 12, comma, true, minus norm dist 22.84, 40, 12, true. And when I simplified that, I should get 70.30. Okay. The next one, I would do a very similar thing. Norm dist 66, 64, 40, 12, true, minus norm dist 56.32, 40, 12, true. That would give us 0737, and you put a box around it. Okay. Next one, what value cuts off the highest 2.33? There seems to be a lot of trouble with this question. Okay. So remember, if I'm cutting off the highest 2.33, Excel is only going to give me what's to the left of it. So I need to tell it, look at everything to the left of it. So if 2.33 is cut off up top to the right, then 100 minus 2.33 is cut off to the left. So that's the z value I want. So I want norm inv, the thing that cuts off 1 minus 0.0233. Now, I don't have to even know what that is. I mean, it'll find it for me. So I don't have to know what that number is. But you just have to plug it in. Or you could put in there 9767 if you wanted to, comma 40, comma 12. And when you do that, you're going to get 63.88. Okay. There we go. D. Oh, that was D. I'm sorry. So if that was D, I probably need to go back and do C. Okay? So for C, what percent of the data is less than 16.24? Well, that's easy. I can just do 16.24 in my norm dist. All right? So I'd have norm dist of 16.24 with a mean of 40, a standard deviation of 12, and for some reason we just plain don't need the word true. And you'd end up with 0239. There are, of course, other ways you could have done this. You could have found the z-score for 16.24, minus 40 divided by 12. Don't know what that is off the top of my head, but once you found that, grab your z-table and just read off what it says on that first table. And then finally we have E. Okay. So E is, what does E ask you? What's the probability that a value is greater than 40.72? Here again, we want to look at what's to the right. Norm's dist will give me what's to the left, so I need to say 1 minus norm dist. My value of interest was 40.72. 40, 12, true. And I should end up with a number of 4761. And that is question number 3. Okay. All right, so I'll leave that on there for a couple of seconds before I put on question 4. Okay. All right, let's keep on going. Question number 4. There are only 2 questions on question number 4. The idea of this question is to show you that you have one where you have a single individual and the other one where you had an average, which means you had to take the central limit theorem. So I have a distribution, normal, 660, 35. And what I need is the area that's more than 670. I could draw the picture, and just for argument's sake, I will draw the picture. 670's here, 660 here. I'm looking for this area right here. I could find the z-score and then plug it in with my table. Or in this case, I want to use Excel. Now the area is norm dist, right? So norm dist, 660, 670, 35, true. This will give me the area that's less than 670. I want the area that's greater than it, so I need a 1 minus in front of it. And when I do that, you'll end up with, let me put true a little bit further over, so I can save some space. When I do that, I'll end up with a number of 0.3875. Okay. That's it for letter A. Now B, I actually could keep the same picture because I haven't changed anything. Only thing that's different now is that I need the central limit theorem to help me with my standard error. So rather than have a sigma as my standard error, I now have sigma over root n. So the actual formula is very similar. B, now you know what? I'll just put B down here since we have space. So if I slide it up some. So for B, I have 1 minus norm dist 670, 660. Here, 35 divided by the square root of 10, because I have 10 samples, okay, comma true. And when you do that, you'll get 1831. Which is your answer. Okay. So compare the differences in probabilities in terms of how variable your data is. You have a much larger chance of getting a value that high looking at one item as opposed to if you're looking at multiple items. So you shrink it from 38%, 39% to about 18%. Almost cut it in half in this case. That was it for 4. Let's keep on moving, and we'll look at number 5. Number 5 is actually the easiest one of them all, because all you had to do was open up Excel and plug in the numbers and see what you end up with. Okay? If you looked at norm dist 56.36 true, this is giving you the area that's less than 5 of a normal distribution centered at 6.3 with a standard deviation of 0.6, and you'd get a number of 0.151. The norm's dist of 0.56 is looking at the z-value that cuts off the lowest 56%, so it needs to be positive, and so you'll have, what will you have? 7123. And I said that completely wrong, so let me actually fix that. Norm's dist actually will tell you the area that's to the left of z is equal to 0.56. That's what I meant to say. Now, norm's dist of 1 minus 0.56 gives you the area to the left of 0.44. So that number just happens to be E. Norms in gives you the area, the z value for that given area. So I want the area, I want the z value that cuts off the lowest 56.36% for for letter 3, number 3, and you'll get that at letter D. Okay. And then 1 minus norms dis of 0.56. Once I get my area that's to the left of 0.56, I subtract that from 1 and end up with the area that's to the right of it. So that's B. Okay. That's it for number 5. I keep on doing that, thinking that this is the regular board. Didn't mean to do that. Okay. Let's keep on moving to number 6, letter 6. What is that? It's a number. Number 6. Okay. Determine if the statement is true or false. Statistical significance automatically implies practical significance. Most of you guys correctly realize this is a false statement, because if I want to have statistical significance, all I have to do is take enough samples and the difference will be in fact significant. It might not be large, it might not have any practical significance, but if it's based on a sample of 1,000 or 2,000 or 30,000, a difference of 0.2 will be significant after a while. So no, statistical significance does not imply practical significance all the time. B, a significant finding at 95% confidence level will be significant at 99%. This is also false. Okay? If you look at the table, or you think about it, if I have more confidence in something, then clearly I have less confidence in it. But if I have less confidence in it, there's no guarantee that I'm more confident in it. And you can see that with the t values, because what happens if you look at as you go across the line, you'll end up seeing that the critical value of t that you have to get over gets larger and larger and larger. So say, for instance, when you look in the column with 95%, you'll see 2.3. That means that in order to become significant, your calculated value has to be larger than 2.3. But when you look at the 99%, that number could be 4.6. So if you had a critical value of, say, 3.5, that is bigger than 2.3, but it isn't bigger than the other number. So you do not necessarily have 99% confidence if you have 95% confidence. The likelihood of finding a significant finding will increase by decreasing the sample size. Now we all know that's wrong. Okay? We just said from A, if I take more samples, I'm more likely to find a significant finding. So it's actually the opposite. If you increase your sample size, you're more likely to find an increase in your significant finding. The distribution of sample means is less variable than the original data that they were based on. This is in fact true. If you remember sigma versus sigma over root n, okay, n is a positive number, it's the sample size. Square root of n is a positive number, it's based on the sample size. So I have a positive number in the denominator versus over 1 for the other denominator. So as long as I'm taking a fraction of a value, in this case 1 over the square root of n, times sigma, that variable is less than 1, which means that it's less variable than sigma itself. So no, so yes, in fact, the distribution of the sample means is less variable than the regular data, because sigma over root n is less than sigma. Okay. Because n is greater than 0. Okay. E. A large correlation coefficient automatically implies statistical significance. This is false. Okay. A large correlation coefficient, if it's based on 2 items, isn't large enough to say that in fact that there is in fact a relationship. So you want to make sure you pay attention to the size of your sample, and you can look at the t statistic to figure that out. Okay. I have more true-false. I'll keep on moving here. Number 7. The correlation coefficient measures the strength of the linear relationship between 4 quantitative variables. There's no way you should have gotten that one wrong. The answer, of course, is false, because it is 2 quantitative variables. If I calculate r equals negative 0.85, then I automatically know I made a calculation error somewhere? No. 0.85 is a valid value for r, because r can range from negative 1 to positive 1. So negative 0.85 may represent a strong negative linear relationship. If a correlation is negative, I cannot represent a strong linear relationship. That's false. Okay? I just showed you a negative correlation that had a strong relationship. 0.85 is one. So just because it's negative does not mean it can't be a strong relationship. D. A horizontal scatter plot implies the variables x and y are uncorrelated. Okay? Now this is in fact a true statement, and here's why. If you think about a graph, okay? The graph has a slope of beta 1, and we said beta 1 is rsy over sx. Now, sy and sx are positive numbers because they represent the standard deviations of the y and the x variable. So these can never be 0. Okay? But a slope of 0 means that it's a rise over run, right? So you have, as I go over to the right, I don't go up at all. So I have a 0 over x to give me a slope of 0. So it doesn't matter how far over to the right I go, I'm at the same level of y. Well, if these can't be 0, if these do not equal 0, then the only way I can get to 0 is if I have 0 times that. And that is what your correlation coefficient can be. So 0 times anything is 0. So the slope of 0 is a flat line. In order way for that to happen, you'd have to have a correlation of 0, because sx and xy can't be 0. And since I have a correlation of 0, that means that the data are uncorrelated, and by definition, the x and y are not linear related, so the answer is true. Now for E, this is also true. Okay, the difference here is something that you guys kind of botched on the test a little bit later on. Come on, there we go. But the amount of variability that's explained by your model is your r squared value, not your r value. So if r is 0.8, then r squared is 0.8 squared, which is 0.64, which is 64%. So if the correlation between x and y is 0.8, and I create a regression to try to predict y from x, 64% of my variability will be explained by my model, and 36% will be left unexplained. So this is in fact a true statement. All right, that's 6 and 7. Let's keep moving. Let's see what number 8 gives us. Match the correlation coefficient with its descriptor. Okay. Here's another issue with the test. I actually have a typo. Okay. This 0.767 here is supposed to be here. Okay. So this is supposed to say negative 0.767. And that 0.588 is supposed to be there. So I ended up taking the square of the determination rather than the square root. But the other 4 were exactly correct, which means that even if 2 was wrong, you still could have got it by process of elimination. So at first glance, you're probably thinking, how in the world would I do this? Let me show you. Okay. So your first question is, how do I solve it? Okay. Let's take the one that's probably the simplest to do. A strong linear relationship between x and y. Strong means an absolute value. It has to be greater than 0.7. This isn't greater. 1 isn't greater than 0.7. 2 isn't greater than 0.7. Actually, it kind of is. 3, 4, 5. Between 2 and 5, I would give this the strong linear relationship. Okay? 0.9 is stronger than 0.7. Okay? and it may be a little bit of a guesstimate considering you had 0.588 there before, so 0.9 is definitely larger than 0.588. Okay. Now for number 1, I have R equals 0.36. Well, if you look at this one here, this is in the standardized form where the correlation is in fact the slope, so we know that this one is D. Okay. I told you 2 is A. Okay. And now how would you get to E? Okay. For E, you'd have data. You would do equals Correl, your data, and you'd end up with E, you'd end up with something along the lines of 0.610. Or you could have grabbed SPSS and gotten it. So this is E. Now for B, that answer is 3.32, and I'll show you how. If B is R SY over SX, and if I solve for R, I have B SX over SY. And when I plug in my values, you'd see that I end up with 0.32. So this is B. Okay. That's it for that. Let's go to number 9. Okay, so here's the part that we may have found is a little bit more difficult, but in actuality, it was actually a little bit easier than the other ones. Okay, so we have these two variables, basically studying and grade on test. Okay, would you believe I made this data up off the top of my head? And look at this correlation. And this is 0.934. This is pretty impressive. I'm pretty proud of myself there. Okay, so I gave you the model output. I gave you the regression here. Okay. You can see the regression here. So for every extra hour of studying, you can expect to do about 2.6 points better than before. Okay. So I do not think I have anything else on this page. Let's go to number 9. Okay. So for number 9, for every additional hour, how much would you expect, how many more points do you think you should get? And so we saw that slope of 2.54. The answer is 2.594. So the answer is 2.594. So about 2.59 points extra. Okay. What score should a person who studied 4.5 hours get? Now, I would have accepted 2 answers here. If you looked at your output, you see the value is 62.53. That's the one that I was expecting. But some of you guys took me a step further and recognized that this was the prediction interval and recognized that, hey, that person can score anywhere between 48 and 77. So either one of those were correct. Now, having said that, it actually lends me directly to question number C, which is, if they studied 4.5 hours, would it surprise you if they got a 70? And the answer should be no. And the reason why is because 70 falls in their prediction interval. So if you had a very slight change of a slope, it's very likely you could end up with 670 or 72 or 74 or whatever. And keep in mind, the previous output gave you the 95% confidence interval of the slope, not the prediction interval. So what that told you was how far that the slope of the angle would alter. And based on that slope, as you progress out, how, once you look at your x equals 4.5, how much does that range? That range based on the confidence interval of the slope gives you a prediction interval, which was here before as LICI and UICI. So no, it shouldn't surprise you. Okay. Sally studied 14 hours and scored a 92 on the test. I'm going to bring this down because I'll show you where Sally is. The purpose of this was to actually show you the data, have you use the data. This is Sally right here. Okay. So did she do better or worse than expected? This third column is her predicted value, which was 87. So she got a 92. She's supposed to have gotten an 82. she did about 5 points better than expected. Uh, I'll just say 5 points better. Okay. Now, E, about what percent of the variability in the test grades are not explained? Okay. I didn't copy it on this page because I'm kind of running out of space on this page, but you may have remembered the correlation of this was 0.934. So if the correlation is 0.934 and the coefficient of determination is 0.872, that's the amount that's explained variance. So if I want the unexplained variance, I have to subtract that from 1. So 1 minus 0.872 is 12.8%. So about 13% of the variability in Y is unexplained by X. Now this is a very interesting point, because the next question is, do you think it's a decent predictor? And the answer to that is yes, for a number of reasons. For one, the correlation is 0.934. I mean, it's almost perfect, really. So that alone would tell you, yeah, I think it is a pretty decent predictor. But I want to focus a little bit on this 12.8% here, because you're looking at one variable, amount of hours studied, and I can get most of my variability, which means I basically can predict the value of my test grade within some error. Now, what if I can add another variable that I had information on? Like, for instance, what if it was a math class and I had their SAT scores when they entered college? Okay? Maybe that can give me an extra 5 or 6 point bump, so that I now can get maybe only 5 or 6% left unexplained. If I do that, I'm using more than one independent variable to predict my dependent variable. So, and this is a little bit of a detour before we get to R, but what that basically means is, in algebra you had y is equal to mx plus b, because you were relating one independent variable to one dependent variable. We here in statistics write y is equal to beta 1x plus beta naught for a reason. Okay? In this case, beta 1 is the slope of the first variable. Okay? But if we added another variable to try to predict, maybe try to use shoe size, maybe try to use number of kids or number of hours worked, because we believe that the number of hours worked is inversely related to your chances of doing well on a test, because you don't have any time to study, that you can actually add another variable there. So it's not just beta 1, but you also have beta 2. Okay? So this could be hours studied, okay? And this could be number of hours worked at a job, okay? And you're still trying to predict here your grade. This is called a multiple linear regression, and this is what you'll get in Quant 2, basically the next semester of this class. So it's important for me to actually show you, because a lot of the research that you'll see in the education field will in fact use multiple values to give you a prediction of y. Now, having said that, your prediction changes a little bit, because before you could say here, in this case here, the interpretation of your slope is for every unit increase in x, then you'd have m increase in y. Okay? When you have multiple values and multiple independent variables, then if I'm looking for the slope of this one, which is x1, the interpretation of this is, if I assume that x2 is constant, so I basically leave it constant, and most of the times we say it's constant at the mean of x2, okay? So if we assume that this is constant at a particular level, then one increase in x will give you beta 1 increases in y. Okay? So I just put that up there because you're going to end up seeing it in Quant 2 if you decide to continue on. So I'm going to erase this now, okay, just because I need some more space, and I'm actually at the end of my form here. And then question number 10. Okay? So question number 10, I have a correlation, and I say, is it significant? And most of you guys got this wrong. You said that it's only based on 19, so no, it's not significant. But what I was getting at this point was to realize you have to actually test its significance. So a correlation of 0.643, to find out if it's significant or not, we have to use that formula that I gave you in class on Thursday, I believe. So you use T is R n minus 2, 1 minus R squared. In this case, you're looking at 643, 17, because 19 minus 2 is 17, 1 minus 643 squared. When you simplify that, you'd end up with 3.46. At this point, what you'd have to do is grab your T-table and look at the line that says 17 degrees of freedom and go across. If you go all the way over to the 99th column, 99th percentile, you'll see a critical value of 2.10. Okay? Well, since this number is greater than this number, then yes, it is a statistically significant value, coefficient, because I'm 99% confident that this correlation is not 0, right? So that's important, because if the correlation is 0, that means that it's unrelated. The whole purpose of the correlation is to see, is there a linear relationship? It could be a weak one, it could be a strong one, but yes, it is in fact a relationship. Okay? So since your critical value is greater than 2.110, you are confident, and at least 99% confident, that there is in fact a statistically significant linear relationship between your two variables. Okay, so that's it for quiz number 2. I'm sure you guys will have questions for me on Monday. Look forward to hearing from you guys. Talk to you soon. Bye.